scientifiques, I would like to start with the blackboard and prepared some lecture notes. So you can download them now. It may be still a dynamical document in the sense that it is missing references. I only put them by putting names and years because I was late preparing that and only finished yesterday night. But the essence is already there, so you can download them and maybe take notes. And then I will switch to, for the second half of the lecture, to the computer. And the second, I think I have 3 disclaimers. The second disclaimer, in this first half, I will also talk about theory while I'm a poor experimentalist, okay? And that means that probably some of you know better, and I'm happy to have comments because I'm also still learning about what I will be presenting, okay? But still, I'll do my best. And the third thing is that I will focus on the second order coherence function and will actually, in the experiments from my group that I will be presenting in the second part, focus on systems with few excitations, okay? And in that sense, I feel a bit intimidated by following a talk by Isabel and David about many body physics, right? So I should still say that we do by now also some experiments in the many excitation sector of photons, which I will not present, but there's Johannes there who is waving his hand and who will give a talk on Friday about experiments where we leave this few excitation regime of atom-light interaction. Okay? And as I say here, I will focus on the second order coherence function. I should somehow keep track of time. Okay, it's 11. And this second order coherence function is actually very useful and powerful because it allows us to quantify the statistical properties and distinguish between different types of light fields, looking at the intensity correlations of the light field. Okay, and the standard definition in quantum optics for a single mode field is that we take the expectation value of the following expression here, and then, right? And we normalize this by the, say, intensity. So we have A dagger of T, A of T here, squared. And loosely speaking, this function gives us the probability for detecting a photon at time t plus tau, if the first photon was detected at t. The way it's normalized is that we compare that probability to the probability of detecting a second photon, provided that the photons are completely uncorrelated. So G2 equals 1 means that it's as likely to have the second photon as in the uncorrelated case, meaning nothing has happened if we detect a first photon. And I mean, many things that I will say about this you can just look up in textbooks, right? But so I would like to share a few things that, at least to me as an experimentalist, have occurred over the time and may have surprised me. What is known is that here you have this normal ordering of the operators, which actually naturally arises because we are considering the detection of light, considering the response of a system which reduces intensity by absorbing photons. And when I do that, then I get this ordering where the positive frequency component of the light field enters. And however, if in principle, hypothetically, if we had rather than a detector which corresponds to an atom where we like expel an electron by absorbing a photon and detect that electron, and one can really model this function here by like writing down the interaction Hamiltonian of the light field with such a atom which is then excited. If we had a detector which was based on stimulated emission, okay, so where the emission caused by the incident light field changes the atom from the excited state to the ground state, and we detect this change, then it turns out that this ordering of the operators goes from the so-called normal order to the anti-normal order, and then the correlations that you find are not the same. And then, however, for example, it turns out you can just work out that if you change the order here from normal order to anti-normal order and take a coherent state, you still find this function to be equal to 1 for all times. Okay, so while the intensity and the correlations, the unnormalized correlations may change, due to the normalization, we would still find the same G2 function here. Okay, so now this just a few examples for this function here. It allows us to quantify the photon statistics, and for example, if we deal with coherent light, then we have a G2 function at tau equals 0 of tau actually, which is 1. So I should have a 1 here. And for thermal light, so for example black body radiation, we know that G2 of tau equals 0 in that case equals 2. And here in that case we speak about bunching. Now this is possible for a classical light field, but then when we have a single photon source, then ideally the probability for having a second photon, provided that the first one has just been detected, is 0, and in that case we have anti-bunching. Okay, and now here I already said that this is maybe not possible classically, but I would like to go through the different criteria based on this second order coherence function to quantify the photon statistics of a non-classical light field. Whoa. by looking first at the classical second order coherence function. So if we look at the classical version of this G2 function, then we are actually correlating intensities. Okay, so I have I of t and I of t plus tau here, and I normalize that by the intensity, average intensity squared, right? And then if we look at 0 time delay, for example, then this is just the ratio of the mean of the square of the intensity over the square of the mean of the intensity. And now we can, in order to evaluate the ratio here, we can imagine that we have a series of n measurements of this intensity here, and then there are 2 ways of calculating the this mean here, either the mean of the square or the square of the mean. And if we take the mean of the intensity, then it would just be the sum of our measurements results for our n measurements, and we divide this by the number of measurements. And if we have the mean of the square, then it's the same thing with a square sign here. And then we can make use of a Cauchy's inequality, where Cauchy's inequality says that if we have 2 times I of t at some instant I ti times a measurement at j here, then this must be smaller or equal to the sum of the squares. So this is Cauchy's inequality, and by using Cauchy's inequality in conjunction with these definitions here, what we find is that this classical coherence function here, second order coherence function, has to be larger than 1 and can be as large as we want. Okay? Then if we, sorry, for tau equals 0. And then if we look at arbitrary times, then since the intensity is positive, we can show that at arbitrary times this coherence function can also go below 1, but is positive, right? Okay. And in analogy to this, so from here I deduce that the intensity, this mean of the square of the intensity, must be larger or equal than the square of the mean of the intensity. And in the same way, what I can show is that the product of the intensities at time t and time t plus tau must be smaller or equal to the intensity at time t squared. Okay, and that allows me to also put, so we here have a bound on the classically allowed values for the classical second order coherence function at time for 0 waiting time, but we can also find from this here that at finite waiting times between the 2 photons, the value of the second order coherence function at 0 waiting time must always be larger than, maybe I blind the screen here, must always be larger, and I think I can put light. So, experimentalist. Okay, so these equations that we have here now put bounds on the values of the second order coherence function for classical light fields, and if these bounds are violated, then we are dealing with a non-classical light field. And we can actually derive now for our second order quantum coherence function criteria that must be fulfilled for the light field to be classical, and I would like to write them down, and at least the third one to me was not so well known, And it's interesting to see that we can actually have 3 criteria from Cauchy's inequalities to distinguish a light field, the quantumness of a light field. The first one follows from here. So we say a classical light field cannot exhibit anti-bunching. So G2 of tau equals 0 must be larger or equal to 1. Okay, so in words, a classical light field cannot exist anti-bunching, and the reason is that the fluctuations of the intensity of a classical light field are bound by shot noise. Okay, so we can not have the variance smaller than the mean. Okay, and then the second criterion which we can deduce here for non-classical light fields is that the value of G2 for a non-zero waiting time must always be smaller than for 0 waiting time. So here, in other words, classical field's G2 function cannot exceed its value at 0 time delay. Okay? If it does so, we violate Cauchy's inequality and thus are not dealing with a classical light field. And then the third criterion, and this can be derived by also taking Cauchy's inequality, but actually decomposing the intensity into the mean value, into its mean value and the fluctuations around the mean value. When we do so, this allows us to derive this third criterion here, which says that this must be smaller, yes, then this. So if we look at this and put it into words, what we see here is that for a classical light field, the maximum deviation from 1 must occur for 0 waiting time. Okay? All deviations from 1 for finite waiting times must be smaller than for 0 waiting time. So these are now 3 criteria for our G2 function, and if any of these criteria are violated, then we deal with a non-classical light field. And it turns out that a number of experimental platforms have violated these criteria here, and the first and seminal experiment was carried out by Jeff Kimball in '78. And if we look at the fluorescence of atoms which are resonantly illuminated with a light field, with a coherent light field, with a laser, thanks. So the setup pretty much still looks the same today that we use, right? So here's a beam of sodium atoms. The atoms are optically pumped. Then you have an excitation laser beam and a microscope objective that collects the fluorescence, and this fluorescence is then sent to a Henbury Brown and Twist setup with 2 photodetectors, and we then measure the waiting times between photon detection events. And then what Kimball, Dagenet, and Mandel saw is that indeed the autocorrelation function here goes below 1, okay, And we have clearly anti-bunching. So we are violating this criterion number 1 for our classical light fields. Now, since then, there's a number of platforms that have also managed to produce non-classical light, but I would only very briefly like to mention some of them and then spend more time on cavity QED with atoms, quoting Kimball, who once in a talk said, atoms are morally superior. Okay, so this is my also conviction, and so we, but I should still mention the other platforms. So we have single atom fluorescence, but then we also have non-linear optical processes. So when you have a nonlinear crystal and pump this crystal with a UV laser, then by spontaneous parametric down conversion, you create photon pairs. And these photon pairs, if you now correlate the two beams, are bunched in the sense that if I detect a photon here, I have one here, but I can also herald on the detection of one photon in this arm, and then I see that I prepare single photon states where I have the probability of having two photons detected is vanishing. Okay, so these were experiments that were carried out in I believe that the first experimental demonstration of such a single photon production by heralding a click here and then saying I have one photon here was done by Hong and Mandel. In 1986. Okay. And then there's also artificial atoms. So to mention quantum dots and color centers in diamonds. And there you have like a very high purity single photon states that can even be emitted in a triggered way. And when I looked it up, then it seems that both the quantum dots and the NVs had their seminal works about anti-bunching and single photon production in the years 2000. And I believe that it was Peter Michler who was the first author of the first work for the quantum dots, and Christian Kotziefer the first for the NVs here. Okay, so this is artificial atoms which are illuminated and can be resonantly or off-resonantly excited here. Maybe one insight that we get if we look at the G2 function of single atom fluorescence, then I will also later sketch that, then it will often look like this and actually has this quadratic dependence here as a function of waiting time. Whereas when you look at the G2 function for quantum dots and NVs, which if you excite them non-resonantly, say you have a kind of 3-level system where you first excite to some auxiliary state from the ground state. From here you may have some non-radiative decay, and then here you have the photon that you detect, then you will invariably see a G2 function which increases like exponentially like this. Okay, and this is because here the underlying dynamics is coherent for the atom, so we are resonantly driving our 2-level atom with light, and we are performing Rabi oscillations between the ground and excited state, and when we detect a photon, then actually the probability for going up to the excited state only increases quadratically with time. So what one can say is that in the dynamics of such a coherently driven 2-level system, fundamentally we have a somewhat longer time interval available where we are sure not to have a second photon, and that can be interesting and helpful for quantum technologies, for example. Yes?
You know why in the Kimball paper we
Yeah.
didn't expect that?
So why does it look like this? Actually, there's a later paper where they improved and have it also, and the theory also says so. I think that here it's also the dephasing, because you have a beam of sodium atoms which enter, and you're renewing the sodium atom all the time, and I believe that induces the same kind or a dephasing of the signal that you are detecting, pretty much in the same way as the quantum dot who loses its memory each time that it gets hit by a phonon. So I think that here this system is still dominated by dephasing because of this beam of sodium atoms with atoms that probabilistically arrive here at random times. And there is a 79 paper, I believe, where they managed to have a function that both experimentally and theoretically also looks like what I sketch here. But if you look at the modern experiments where you really have an atom in a dipole trap or an ion or a molecule, for a molecule again it depends whether you excite it resonantly or off resonantly, but you will see this coherent dynamics. So this is something, as I said, that is important to keep in mind, that the coherent driving of an atom gives rise to a different G2 function than for incoherently populating the excited state. Okay, and then as I said, I very quickly covered and didn't pay due respect to these experiments here, just to move on to cavity quantum electrodynamics, where, according to Jeff Kimball, he termed that the one-dimensional atom, because in these experiments here, that you are illuminating the atom and the atom emits into free space, into all directions, whereas if you now put the atom into a cavity in the so-called strong coupling regime, then the Purcell effect makes the probability for the excited atom to emit its light into the cavity mode much larger than into free space. Okay, and in this case, if you now send light and couple it to the cavity, you may look at the transmission of the light through that cavity. Then you have like an interaction of such a single mode light field with an atom or an ion or a molecule which is strongly coupled to this light field. Okay, and then I will say a few words of how to calculate it, but before just explaining how to calculate it, I would like to flash more recent data. So the first PhD student of Jeff Kimball that, according to what he says to me, finished his PhD with Jeff Kimball, which was not the first PhD student of Jeff Kimball. So the first PhD student that finished his PhD with Jeff Kimball was Luis Orozco, and Luis Orozco did very early work on this photon statistics of the light that is sent through such a cavity QED system with in the early works it was the same as you see here, with a beam of atoms that was transversing the cavity, so you had a fluctuating atom number also in the cavity, and he could show non-classical behavior of the light field that was transmitted. But I would like to highlight work from Wahid Zandokdar's group. There was a PhD student, Daiking Wang, who set up an experiment with a single dye molecule coupled to a microscopic, really, really small Fabry-Perot cavity. So the mode volume was much smaller than what you usually achieve. He had the molecule on a substrate. So here there is a dye molecule on a substrate, cooled down to very low temperatures, and then he had a micro mirror here on an optical fiber. So there's these fiber cavities with a core here, and then he measured so he focused light onto the molecule, which went then through, and this here is a mirror, this substrate. So I have a plane mirror, a molecule, and a curved mirror here, and I have a mode volume which is only on the order of a few cubic wavelengths, which increases the coupling strength. And then Daiking Wang looked at the photon statistics of the light that was transmitted through this system. And now you can tune the parameters of your experiment. You can tune the frequency detuning between the molecular transition and the cavity, and you can also tune your laser frequencies. You have two detunings, laser with respect to cavity and molecule with respect to cavity. And if you look at the general transmission spectrum here, I mean, the transmission as a function of laser detuning, so here I have omega laser, then you will see such a Lorentzian transmission spectrum through the bare cavity, right? And if I now place a molecule inside, and let us assume that the molecular transmission or the molecular resonance is narrower than the cavity resonance width here, then we will have, depending on the atom cavity detuning, change of the spectrum. Maybe I have a different color here, where the spectrum of the cavity will split, and we see the molecule showing up as a drop in transmission, because if the molecule is strongly coupled, then in essence it's as if at resonance I was putting my finger into this cavity, okay? And in that case, the light that comes in here only sees this highly reflecting mirror from the entrance here and is reflected, and no light exits here, okay? Saying that, it already indicates that much of what I see in this structural spectral features that show up in such a strongly coupled cavity QED system can be understood classically, okay? So I can derive this spectrum by just putting a classical dipole into this cavity, Lorentz oscillator, which absorbs light and also imparts a phase shift on the light if I off-resonantly drive this classical dipole here. This is why there are like two resonances shifted with respect to the bare cavity resonance, because I have a phase shift, additional phase shift upon round trip, which shifts the resonance frequency to higher and lower frequencies. So I can explain most of what we see here just talking about a classical dipole in a cavity. But then what Daiking Wang did was to study the photon statistics of the light that was transmitted here. And actually I will show several data where what was done was to change the frequency, the tuning between the cavity and the molecule. So the spectrum may look like this, but it may also look, for example, for a larger detuning like this. Okay, so where and what he did was to always tune the laser to this transmission peak here, to the low frequency transmission peak, and looked at the light going through this system. And doing so, he observed violation of the three criteria I will walk you through that we wrote down for the non-classical light field. Okay, so this is for relatively large atom cavity detuning, so for a case that looks like this here, okay? And the blue solid line gives the value of G2 at 0 waiting time. And this dashed line is 2 times G2, no, it's G2 minus, G2 plus 2. 2 times G2 plus 2. Wait. It's 2 minus G2 of 0. So this line here is 2 minus G2 of 0. And that relates to this third criterion, saying that the deviation of the second order coherence function from 1, look here is 1, okay, must be largest at the 0 time delay, but actually the deviation is both possible positive and negative, and this is why we have now a band here inside which, by this third criterion, the values of my second order coherence function are confined. Okay, and if they leave this band of values, then I violate the third criterion. And then, well, what we see is that indeed we have G2 of tau equals 0 negative. So this violates the first criterion. Smaller than 1, exactly, G2 minus 1 negative. So smaller than 1, this violates the first criterion. We have G2 of tau larger than 0, smaller than G2 of tau at 0 waiting time. And we go outside of the classically permitted value bands here. Okay? And now look what happens when we now change the detuning and go from this molecule-like transmission peak here and we shift the molecule atom detuning. Then this is for smaller atom molecule detuning. We still have all three criteria violated. We are below 1. We have larger deviation, smaller values for finite tau than for tau equals 1. And we leave the allowed band of values. So still all three are violated. But then here, for example, and this is why I highlighted this third criterion, this is a G2 function which neither shows anti-bunching, because G2 of tau at 0 waiting time is larger than 1, so this is classical in that sense, okay? And all values of G2 for finite tau are smaller than G2 of tau equals 0, so this is also classical from that respect. But if we look at the classically allowed value range according to the third criterion, we leave this value range here, okay? So this is non-classical, but just because of this third criterion. Okay. So now I somehow have to check how I'm doing with time. So I did a bit more than half an hour, so that's good. Then I will now finish by saying a few words, and again, correct me if I talk nonsense about how. So here you see that there are theory predictions for the G2 function. So how do I actually calculate such theory predictions for the G2 function? And there are, depending on the system and its complexity and properties, there may be different ways, and I would like to just very briefly mention them and show what they have in common. So the first theoretical approach to calculating G2 can be applied for a system, for an open quantum system, which is described by a Lindblad master equation. And I just briefly write it down to have all the quantities on the board. So we have a Liouvillean super operator that acts on our density matrix rho here, and that I can write as minus I over h bar times commutator of h and rho. And then I have my Lindblad stochastic jump operators that act on our density operator, and I can have different loss channels, so I have to sum here over the different possible loss channels. Minus 1/2 times, and then the anticommutator of LK dagger, LK rho. So if our system is described by this Lindblad master equation, then the quantum regression theorem allows us to also compute, using the same Liouvillean here as for the time evolution of the density matrix, 2-time correlation functions. Okay, so we need the quantum regression theorem, and this quantum regression theorem then allows us to compute these like correlators at different times, and the way it is done is to take the, I first maybe write down the expression, and then we go step by step through what is done here. Okay, so let us go step by step through interpreting this expression here. So what we have is, first we have a system which is prepared at time t and is represented by this density matrix rho of t. And then we have an operator, like a measurement, acting on rho, and we get a conditional state here, okay, which at time t is like changed by this measurement of our operator A. And then comes the quantum regression theorem and says that I can now propagate this conditional state here, this conditional rho, through time over the time difference tau with the same Liouvillean super operator as the one that is used for propagating the density matrix in time. Okay? And then I have my state at time t plus tau and calculate the expectation value of my operator B at time t plus tau. Okay, so this is the way we use the quantum regression theorem, and there are like preconditions or that enter in for this to be valid, what I presented here. And I don't know if I will say all of them, but the most important one is that there's no memory in the environment, so that actually the fact that I performed this measurement here does not alter the environment, meaning that there's no memory in our Liouvillean here, and I can actually use the same as for the density matrix, for the propagation of the density matrix in time, okay? And now I would just like to say how we use that to calculate now our second order coherence function. Well, so G2 of tau is calculated in the following way. First, we have like the initial conditioning here. The initial conditioning, so our rho conditional, is given by the action of our annihilation operators onto the steady state density matrix of our system. So I have my cavity which is driven, I send my light through the cavity, and then I detect a photon. And that prepares, so to speak, a conditional state, rho conditional, which looks like this. And then I do time evolution, and the time, so this is step 1, then the second step is the time evolution, and for that with that I calculate my state at time t plus tau, and this is done by applying the Liouvillean time evolution here to this steady state, to this conditional state. And then we compute the expectation value of my operator A dagger. So I just take this A of 0, A dagger of tau, A of tau, A of 0 as the trace of A dagger A times rho of tau. Okay? And then I take this and normalize it for the unconditional state here, and then, so I just say 4 is normalization, and I'm done. And I went through this to actually highlight because there are other ways that you can also use for calculating G2, but in the end it always is very physical, right? Or it is very intuitive what we are doing. So we detect a photon, and then we ask what is the probability for detecting another photon. Well, then we have to see how the system evolves after the detection of that photon, and then compute the probability for detecting a photon after that time tau. Okay, and this can be either done using this master equation and quantum regression theorem. There are other methods, and I would like to highlight one because it's also very intuitive and really a physical picture of what is happening. And also there I learned something not so long ago which I was ignoring, so let me share that with you, which is the quantum jump, or Monte Carlo wave function method. So the Monte Carlo wave function method means that we are actually propagating our density matrix in time, but we neglect the stochastic jumps, and we introduce an effective Hamiltonian which only contains the dissipation because here, but not the stochastic quantum jumps. And so this is the Monte Carlo wave function method. So here I actually use an effective Hamiltonian, and this effective Hamiltonian is given by the H that we have here, and then only this part here of my master equation. So that can be written as minus I H bar over 2, and then the sum of all dissipations. Okay, and now I use this effective Hamiltonian, and I consider that I initialize the system at time t equals 0, and then I propagate the system over the time, a very short time, delta t, with this effective Hamiltonian. And this effective Hamiltonian then gives me a new state, and my state at time t plus dt, this state here, is then given by, to first order, 1 minus I times h effective times dt over h bar acting on psi. And what we do is we normalize, because this effective Hamiltonian is not unitary, it does not preserve the norm of our state. So we renormalize by the same state here, okay? The norm of this state. And then we calculate the probability for a quantum jump to occur by looking at the loss of the norm of our state vector due to the propagation over the small increment of time. So calculate the probability for a quantum jump. And we draw a random number. And if the random number, let's call it R, which is drawn between 0 and 1, is smaller, so let's call that a quantum jump into the channel K, let's call that probability pk, okay? If this number is smaller than the sum of all probabilities of having undergone a quantum jump, we apply a quantum jump. And this quantum jump then prepares a new state, which is given by this expression, and again we normalize by the norm of this vector here, okay? And then we repeat steps 2 to 3, okay? So we do this over and over again until we reach the final time, capital T. And then, so how do we get now, I mean, this is actually the trajectories that we calculate, right? So we have evolution of the system, quantum jump. So maybe if we plot the probability of the atom being excited here, then it's driven, it oscillates, and then all of a sudden, boom, I have a quantum jump, and then I have another quantum jump. So this is one trajectory, right? Now you can compute the density matrix from averaging over many of these trajectories. But here we're not interested in the density matrix, but we're just interested in the second order coherence function. And the second order coherence function can then be easily computed or constructed by a histogram of time delays. So this is done by looking for each quantum jump that occurs at a certain time. We look forward in time and ask what time elapses to the next quantum jump. And then we do a histogram of these waiting times. So histogram of time delays. And then normalization. And when we normalize, this gives us, because, okay, this histogram of time delays gives us the unnormalized second order coherence function, and then the normalization gives us the second order coherence function, right? And here again, and what I would like to stress that because it's the starting point for the second half of my lecture, yes. I would like to make clear here that again the underlying physics is the same in a sense as here, because we have this initialization of the system by a first measurement event, okay? And then we have time evolution, and then a probability for detecting the second photon. And the same here for this Monte Carlo wave function method, right? We have a coherent evolution, but what I would like to stress is that other than one might think, the coherent evolution is not governed by the system with, by the Hamiltonian that describes the system without dissipation. So it turns out that the coherent evolution takes place with a Rabi frequency that is different from the resonant Rabi frequency of the laser, because we have this dissipation term here. Okay, so this is some important insight that it took for me 20 years to have it. Actually, I always thought like, I do as if there was no quantum jumps, but that meant for me also I do as if there is no dissipation. But we actually in this dynamics that comes from this effective Hamiltonian, dissipation is there, and we just leave the stochastic quantum jumps out, and those are then like done in a Monte Carlo method by drawing a random number and asking, was there a quantum jump? And this method is actually very useful if you have few quantum jumps and few excitations. Then it is more less costly computationally than the full description. Okay, and with this I'm done. I hope I defended myself well. Maybe you have comments. If not, then I think this is a good starting point for now giving you a different view on the second order coherence function, which we recently had and which were inspired by theory work as so often. And where the insight that we gained inspired real experiments that are not so obvious when you have just the picture that I showed you so far. Okay? So, yes?
Yeah, I have a question regarding the criterion 1, because sometimes in papers you see people, they quote G2 of 0 greater or equal than, less or equal than 0.5.
Yeah.
To demonstrate quantum.
So I think, so the question is it quantum if G2 of 0, does it have to be smaller than 0.5 to be quantum? And my understanding is that this criterion here shows you that you are dealing with one emitter, not two. So if you have more than one emitter, then you will have values that exceed 0.5, but the field that is emitted by two emitters that are driven and where you collect the resonance fluorescence from two emitters is still non-classical. Okay, so this criteria, and interestingly, I think maybe you will show that this is actually not even true. So I think you can actually have smaller than 0.5 with two emitters if you are Joachim. Okay. So look, wait for us. Huh?
If you have an ion trap, not
okay. If you have an ion trap. So you will talk about that, so then I don't have to elaborate on it, right? So, but the standard wisdom has that, okay? That one says this is a smoking gun for a single emitter, and if you don't do efforts, it's a good criterion, I think. Okay. Good. So now let us look at anti-bunching and resonance fluorescence, and I can race through that because we said if we drive now a single emitter, already Kimball did that, and here for simplicity we assume non-resonant light field, near-resonant light field and weak driving, so the intensity does not saturate the emitter. Then if you look up in textbooks, then you see that the scattered field features a so-called coherent and incoherent component, where the coherent component scales with the intensity and the incoherent component scales with the intensity squared. So here you see that this incoherent component must come from some non-linear process, okay, because it scales with the intensity squared. And if we then look at the G2 function, then we see this characteristic anti-bunching behavior if we have our molecule or atom or ion illuminated. And that means that the probability for detecting two photons simultaneously is 0, and I said that that we can say that with certainty is because we are standing on the shoulder of giants, and in this case on Jeff Kimball's shoulders, who sadly passed away last year, and he had this seminal paper here where he showed anti-bunching in resonance fluorescence. And if you look at the paper and read what they say when they interpret this here, is that they interpret it exactly in the way that I was highlighting when saying how do we calculate this G2 function, okay? Because they say that the fact that this, like, this is a G2 function, it's other characters here, vanishes for tau equals 0 is a reflection of the fact that when the atom has emitted a photon at time t, then it has undergone a quantum jump to the lower state and is unable, therefore, to radiate immediately another photon. And you have to time evolve the system in order to be able to emit another photon. And so, in other words, the probability for detecting two photons simultaneously is 0 could be translated into saying a single two-level atom will not scatter two photons simultaneously, right? And then the rest of my talk is about really? Okay, so is that really true? And again, the reason why I can ask that question is because we're standing on the shoulder of giants, and it's, this is important before going on, because I may run out of time at the end. I would like to thank the people that really did the work. So it's the PhD student Luke Masters and Gabriele Maron and Chin Hu is a postdoc, and they were in the experiment. Then we had Martin Cordier and Max Schemmer, who already got exposed today twice then. And they had a lot of contributions concerning the conceptual interpretation and theory, and then Jürgen Volz, my senior co-worker, was the sub-project leader here. And so all what I will be presenting you now has been worked out by Jean Dalibard and Serge Renaud, who only a few years after this work by Kimball actually reanalyzed these correlation systems signals in resonance fluorescence by saying, let's look at photon scattering amplitudes. And what they found is that you can explain this photon anti-bunching effect as being due to a quantum interference between all the possible scattering amplitudes. And they go on, when Rayleigh photons are rejected, so these are the so-called coherent photons, I will tell you what these are. So if some of the photons are rejected from the resonance fluorescence, then some amplitudes vanish, and then we could observe bunching in resonance fluorescence, okay? And to highlight what they really mean, let me explain that we have this coherent and incoherent component, and the coherent component of the light that comes from the atom corresponds to the scattering of two independent photons. So in both scattering events, energy is conserved. So both photons are carbon copy of the laser light that is exciting the atom, and so the output state is two separable output photons, okay, which have the same frequency and phase as the laser, or fixed phase relationship to the laser. And then there is this incoherent component. This incoherent to photon scattering can be pictured in this way. Imagine that I have a pump photon which is absorbed, and then I actually, within the lifetime of the excited state, I emit a photon. I reabsorb a pump photon and thereby excite my atom, and then it emits a second photon. So in this process, it's a 4-photon interaction. Energy is only conserved in the full process. That means that the energy of this photon and of this photon, the sum of the energies of these two photons has to be equal to the sum of the energies of the two pump photons. And then it turns out that these two photons are no longer independent because they are like entangled in terms of their energy, and we are dealing with an entangled photon pair here, okay? And of course, this has to happen within the lifetime of the excited state, so to speak, for Heisenberg inequality to allow you to do this kind of zigzagging here in the energy level scheme, okay? And so let us call the scatter. So Dalibard and Renaud talked about scattering amplitudes. Let's call the scattering amplitude of that process chi, and it may depend on the detuning of our pump laser and on the waiting time between the two photons that I'm detecting. And let's call the scattering amplitude for this process here phi, okay, which also depends on the detuning of my laser and on the waiting time. And then let me give you the expressions for these two components. For the coherent component, it turns out that this amplitude is independent of the waiting time. It's not surprising. It's uncorrelated photons, so there is no dependence on the waiting time. And we actually have simply a time invariant amplitude which is given by the rate of coherently scattered photons over 2. Okay, so this is the amplitude for our coherent process. So if I sketch that as a function of waiting time, it's just a flat line, right? So this is chi of tau. It doesn't depend on tau. If we now go to the frequency picture, so I Fourier transform this amplitude and ask what is the amplitude as a function of the frequency, then flat line gives the delta function. So, and this delta function is just the laser line. So if the laser has some finite width, then this would be a bit broader, but it's determined, the width is determined by the laser. The thing is different for this incoherent scattering, because here the whole thing has to happen within the lifetime of the excited state. And once the atom, say, is excited by this process, it decays and emits this next photon. So that means that our amplitude here actually depends on the waiting time. It decays exponentially with the waiting time, where gamma is the decay rate of the excited state. And if I'm detuned, I still have some quantum phase here, which also depends on time. But at resonance, we would have this expression here, okay? So that means that my incoherent two-photon scattering amplitude looks like a bi-exponential here. So it gives the probability amplitude for the second photon once the first one is scattered, okay? Yes?
Very short one, maybe for clarification. The tau refers then to the time difference between the two incoming photons.
How it refers to the?
To the time difference between the two incoming photons. I mean, to understand that the green flat line is on the left top is flat. I mean, so it does not depend at which time difference of first.
Exactly.
The green photon.
So for this one or for this one?
For the green one.
For the green one. Yeah.
I just wanted to say.
Yeah. So can you say that again, that I repeated?
No. I wanted to say that the tau, the x-axis for the green curve, for the flat curve, refers to the time difference of the two incoming photons.
Yes, it's correct. So because here, since they are scattered independently, this tau is also, yes, thank you. That's a good way of seeing it. I didn't have that. So indeed, this tau is also the waiting time between the two incoming photons, because the photons are scattered independently. Okay, perfect. Thank you. Yes, that's true. And now here for this, here I plot this incoherent two-photon scattering amplitude, right? And it's this bi-exponential. If we do a Fourier transform of this, then for zero detuning, so if I don't have this term, I will get a Lorentzian. So this is this case here. But if I now introduce a detuning of, say, 1 line width, 3 line widths, or 7 line widths, then this additional phase factor here in the Fourier transform results in 2, let's say, Lorentzians, which are split for large detunings by the detuning, and for smaller detunings by the effective Rabi frequency, which depends both on the resonant Rabi frequency and the detuning. Okay, so spectrally, you see that the incoherent and coherent component have different spectral features, right? That's clear here. And now the total two-photon scattering amplitude is given by the superposition of the coherently and incoherently scattered two-photon component, right? So we have a superposition that gives rise to the total two-photon scattering amplitude. And now let us look at these expressions here a bit more in detail, right? wanted to say that the total two-photon wave function, if I Fourier transform it, then has such a spectrum of 3 peaks if I'm detuned. And this is referred to as the Mollo triplet in the detuned case. Okay, so here I have a two-level system which is near resonantly driven with a detuning delta. Then the light that comes out has this spectrum here, where these two correspond to the incoherently scattered component, and this is the coherently scattered component. So, and now let us look at this two-photon wave function more in detail. And we see that compared to this coherent component, there's a minus sign here. And this is actually a non-linear phase, because it's different for this by a factor of -1. There's an easy way of understanding that. Here we have two independent scattering events. So 2 times I absorb a photon and emit a photon. And when I absorb and re-emit a photon, I get a phase of pi in this process. And then doing this 2 times, I get a phase of 2 pi. And 2 pi is 0, and I get a plus sign here. Here, in this process, I can understand this as the first photon being absorbed and the second photon stimulating the emission. So it just goes through. I absorb the first photon, the second one comes and stimulates the emission. So I only have 1 photon being absorbed and re-emitted, and that gives rise to a phase shift of pi. And then between pi and 2 pi, I have a minus sign. So this is where this minus sign comes from, okay? And then if we look at 0 waiting time, we see, maybe I go back, if I say tau equals 0 here, then these two terms are just unity, and we see that the two scattering amplitudes have the same modulus at 0 waiting time. So here I plot the modulus, but they have a minus sign, so they are, one is the negative of the other. And that means that in this superposition here at 0 waiting time, my two-photon wave function vanishes, right? And then this second-order coherence function here can simply be computed from this two-photon wave function by taking the modulus squared of this two-photon wave function, okay? So that means that G2 of tau is now the modulus squared of our two-photon wave function, which is the superposition of the coherently and incoherently scattered component. And if you take the modulus squared of a superposition, you get interference, right? So that means that it's the interference between the coherently and incoherently scattered photons that lead to this anti-bunching in resonance fluorescence. At least it's one way of seeing it, okay? And then you also see that since in this near resonant case with finite detuning, I can spectrally address these components here. And this is what Dalibard and Renaud suggested in their abstract. They said, so what now if we filter this resonance fluorescence? And it turns out that there was a first experiment where the incoherent component was filtered away. So that was done by, Hanschke et al. Here in this PRL. So they just used a very narrow band Fabry-Perot, right? And they suppressed the sidebands so it's a band pass filter that only lets this component pass. And in this case, the incoherent component goes away, and I'm left just with the coherent scattering amplitude, but this coherent scattering amplitude is time independent, and so I get a flat G2. I would like to stress that this experiment can be understood classically, if you like, because here, if you think of the photons being billiard balls, okay, which are anticorrelated, so they have some finite distance between each other, and I then put something like a bandpass filter, then the response time of this bandpass filter has to be much slower than the time difference between billiard balls in order to be able to filter just this coherent component out and suppress these components. So you have a kind of random waiting time that you introduce between your billiard balls, and you scramble all correlations. But what Dalibard and Renaud suggested was, let's get rid of the Rayleigh photons, the coherent component. And in this case, we are only left with the incoherently scattered two-photon component, and that is this bi-exponential behavior here. And so we would expect bunching. That was what they said in their abstract, right? And I will now present you an experiment where we go from anti-bunching, two bunching in one and the same setup by doing such filtering. Yes?
One question, sorry. Can I have an intuition of what's going to be the spectrum of these side bands? What they should be looking at? Like the blue and the red blobs? Can I know what are the probability of their moment, their distribution in omega?
So I try to answer another question, or no, so just to say what I understood. So I should stress that when we are showing this here, we have to use, in order to see even this so sometimes people say, how can there be interference? Is that your question?
No, my question is, do you know what's the spectrum of the blue and the red?
The blue and the red, yeah, it's the Fourier transform of this function, and so this is the spectrum of the blue and the red. It's the Fourier transform of exponent. If you have very large detuning, then these are two Lorentzians. Yes, yeah, exactly. Okay, so now to do the experiment, we trap a single rubidium atom in an optical tweezer, and we collect the light with the same lens that we use for trapping the atom, and we couple it into an optical fiber, and then we send it onto some single photon counting module. And if you then look at the time evolution of the fluorescence signal, and you see this characteristic telegraph signal where we have two levels, and this level corresponds to no atom, this to one, and we never have two. This is because there's the collisional blockade effect, which ejects two atoms from the trap. Immediately when a second atom enters, both atoms undergo a light-assistant chemical reaction, which is releasing so much energy that, boom, both atoms leave. And so then we know when we are dealing with one atom in the trap, and we can use these times here, which are on the order of 100 milliseconds here, to analyze what is the fluorescence from a single atom doing. And if we now set up such a Henbury, Brown and Twist setup where we measure the correlations between the time correlations between the photons, then we do see anti-bunching. Okay, so here is all this is uncorrected, so we don't subtract background. It's just the normalized autocorrelation function. We have the level 1 is here. You see we go below 1, so we do have anti-bunching. The dark count level is below 0.5, and we reach this dark count level. So we are below this 0.5 by a bit, so it's 0.4. And now the reason why we see these oscillations is because we have a detuning between the laser and the atom, and this detuning leads to oscillations at the frequency detuning, and this frequency detuning for the it's 60 megahertz, but for the expert it comes both from the laser being detuned from the atom in free space and the atom being in this tweezer, because the tweezer actually increases the atomic transition frequency by a bit due to the light shift. Okay, so we have two contributions, and they sum up to 60 megahertz, and these are these 60 megahertz oscillations that we see here, right? And now remember that the spectrum of this, so this is the G2 function of the Mollo triplet, which looks like this, and we would now like to suppress this component here. So we have this spectrum in our resonance fluorescence. We want to suppress this component and leave these two here intact and go through to be to analyze their photon statistics. And for that we need a notch filter which is in the optical domain much narrower than this frequency splitting here, which is 60 megahertz. Okay, so this is a challenge, but we actually managed to do that by putting a so-called a fiber ring resonator. So this is just a fiber loop of a few meter length. It's a ring resonator, and here we have a directional coupler which couples the light from this fiber into the resonator and out again with a variable ratio of coupling. We have a screw, and we can tune that coupling ratio until we reach the so-called critical coupling regime. In the critical coupling regime, the resonances of this resonator show up as dips in the transmission of this fiber, and when we have critical coupling at resonance, the transmission is ideally zero. You can see this here as a 50 ohm connector to your optical fiber. Nothing is reflected, nothing is transmitted, all is dissipated in the resonator. And the nice thing is that since it's a long resonator, we have narrow resonances, and we put up the free spectral range in such a way that when this resonance suppresses the Rayleigh component, the two sidebands fall into the region of high transmission between the two components. Okay, and when we do this, we are only left with this incoherent component. And if we now analyze the photon statistics, we see bunching. Okay, okay, and so here we see a G2 function which goes up to 7 here. Okay, so the probability for having a second photon detected, provided that the first one has just been detected, is 7 times higher than for uncorrelated photons. Okay, so we do see bunching. So let me wrap up. So here we have I showed you that there's in the two photon scattering, we have interference between coherently and incoherently scattered two photon components. If we have this resonance fluorescence unfiltered, their interference gives rise to anti-bunching. If we filter the coherent scattering away using our fiber ring resonator, we have strong bunching. And then I can now ask again this question: will a single two-level emitter scatter two photons simultaneously? Okay, and now provocatively I would say yes, it does so permanently and even in two different ways. Okay, but this is now debatable, as so often in quantum mechanics. But there's one thing that you cannot deny. Okay, that I'm happy to discuss about this interpretation, and I have more slides if you want. But there's nothing to discuss about this statement. What we see is that if we deal with anti-bunch light, because the atom emits anti-bunch light, then we can transform this anti-bunch light into bunch light using a classical linear notch filter. So there's nothing quantum at first sight about this filter. It's just a notch filter made from a linear resonator. Okay, and so in other words, if we remove photons from a single photon source, then this causes the remaining ones to coalesce. Okay, and this is a fun result. So yeah, with this I would like to thank you for your attention, and I'm happy to take questions.